This is a more slightly advanced example of using EQR-opt with Mician Microwave Wizard. EQR-opt, again, is an optimization engine that works in conjunction with Microwave Wizard to optimize Chebyshev filters to a perfectly equal ripple passband. So here's the top level schematic of our diplexer. It's a Waveguide H-plane diplexer. And here are two channel filters. We've just called one transmit and one receive. And if we look over here in the variable list, we have a block of variables for each of those channels. For this filter, the waveguide irises are variables, and the lengths of the waveguide cavities are variables. And we have the same thing for the other filter. Then to define the problem for the optimizer, we have two blocks of reflection zero frequencies here, one for each filter. So we can independently set the center frequency and bandwidth of each of our channels using these frequencies to talk to the optimizer. This is the 3D view of what our filter looks like, our diplexer looks like. And again, it's simplified. We've ignored some details like radii in the corners. We could add some nominal tuning screws if we like. We could also set the iris widths and tune with the lengths of the screws would be another possibility. So to get to this starting point, we designed two waveguide filters on a doubly terminated basis. We put them together with the T-junction, and then we have to do some manual adjustment of this length and this length of waveguide in order to get the starting point close enough for the optimizer to grab it. And in this case, we had to modify the width of the first irises for both channels as well. But that's a relatively fast process, and we can do it with the tuner in Mician Microwave Wizard. So this is what the frequency response of the diplexer looks like for our starting point. Again, both channels are n equals 6, and we only see 5 reflection nulls here in the passband. We expect to have 6 when we finish, but this is a good enough starting point for the optimizer to capture this and improve on the solution. So if we bring up the optimizer, again, the interface is very simple. There's very little to adjust here. The real key to communicating with the software is the list of the reflection zero frequencies. So if we start the optimizer running, for an n equals 6 filter, we have 12 variables. And so because it's a diplexer, we have 22 or 24 variables that we're optimizing here simultaneously. We're not going back and forth between the two channels. We're looking at all the variables in both channels simultaneously. So now it's found a new transfer function for the passband, and it's going to optimize on that a little bit, and we'll see what our first result is. and maybe one more iteration. So with only 7 iterations of the optimizer, we've now see all 6 nulls in the passband of the 2 filters. We're not quite to perfectly equal ripple. The optimization that forces this to perfectly equal ripple is actually an iterative process. So sometimes we have to run the optimizer maybe one more time or 2 more times. But since we're very, very close to the final solution, that goes very fast. And now we have a nearly perfect equal ripple response in both passbands. Now we can control the return loss of each channel independently. It's the width of the output irises that sets the return loss level. So we can modify those widths independently and move our return loss level up and down. So that's an example of using EQR-opt for diplexer design, and of course this scales up to multiplexers as well.